If you could please have a seat, we can start the session. Allora, devo mettere la cosa. Oh, ma perché non va sto coso adesso? Perché non va? Un attimo. Ok, c'hai questo?
Ecco, mancava tu cuoque.
Che Brutus, aspetta. Ah, perché non va però?
The infamous pointer. No. Ok, grazie.
Excuse me. I have an announcement before we start the session. We're going to take the group photo tomorrow at the beginning of the first morning coffee break, okay?
Okay, take your seats. We start the second and final session of this morning with Marco Laurenti, who will tell us about hyperluminous AGN studied with XMM Newton.
So, hello everyone, AGM people, and I want to thank the organizers and also all of you for having me. Today I'd like to talk to you about my research project that involves alley-accreting AGN. So, what we know so far is that, well, the different components of an AGN contribute to the emission at different wavelengths. And specifically, the X-rays are produced by a corona of hot electrons that lies close to the black hole. And what happens here is that the optical UV photons from the disk interact with the corona and are upscattered to X-ray energies through inverse Compton scattering. And usually, the way we quantify the relative strength between the optical UV and X-ray emission is by means of the alpha-X parameter. On the other hand, the way we quantify the AGN accretion activity is by means of the Edenton ratio parameter. And though this classification here on the right may appear somewhat arbitrary in terms of those values, and indeed it is, well, there is no doubt that so far much more attention, as you can see from the plot, has been given to AGN accreting in the low and moderate regimes. So even in those surveys that can rely on very good quality X-ray data, such as BESS. Up to now, high Eddington AGN have been overlooked to some extent, with the only exception of narrow-line C41 galaxies, which, however, represent a very peculiar class of AGN hosting only low-mass supermassive black holes. But the thing is that the whole population of high Eddington AGN should deserve an in-depth investigation for several reasons. The first one has to do with the physics of accretion that, as you can see for these objects, appears to be much different from what happens to the low Eddington counterparts. Indeed, an increasing Eddington ratio, advection gains importance, and we end up with a disk that's both optically and geometrically thick. As also shown before, these sources might also have cosmological implications. Many believe that at least a period of high Eddington accretion can be a possibility to justify the presence of 10 to the 9 solar mass black holes at high redshift when the universe was less than 1 giga-year old. And finally, these sources are also thought to be prone to accelerate powerful disk waves, such as warm absorbers and ultra-fast outflows, that can be capable of affecting the growth and the evolution of the host galaxy where the AGN lives in. Many authors have claimed for the existence of a positive correlation between the Eddington ratio and the photon index of the X-ray parallel continuum gamma, by means of which we would expect AGN radiating close to the Eddington limit to have steep values of gamma greater or equal than 2, and this is often explained in terms of an enhanced UV emission for these sources that makes the radiative cooling in the corona more efficient, and the result is a steepening of the power law spectrum. Anyway, the point here is that this relation elicited immediate interest for one main reason, since it would represent a turning point for almost every extragalactic survey. Whether verified, this relation might allow us to estimate the black hole mass from the X-ray spectrum, given that a reliable measurement of gamma is provided. However, as you can see from the plot, the red shaded area, that's the region where I add into an AGN are lying into, is poorly sampled. And these hampers firm conclusions on these correlations, and it's also one of the reasons that motivated us to populate this area. And the first step was to analyze a sample of high black hole mass, radio-quiet, type 1 AGN, radiating close to the Eddington limit at a redshift around 0.5. This sample was drawn from a larger sample of diacritic AGN from a work by Paula. We selected to have homogeneous optical properties. But what we find is that the X-ray properties are very heterogeneous, starting from the photon index, gamma. Here you can see that 4 of our AGN, that 4 of our AGN are lying at very quite flat values of gamma, around smaller or equal than 1.6, and this is at odds with the expectations based on the relation we have just seen. Not only that, I'd like you to notice that though our sources are lying in a narrow interval of Eddington ratio, well, the scatter in terms of gamma is quite large, and this suggests caution when using these relations to estimate the black hole mass from the X-ray spectrum. Another interesting thing comes when we look at the alpha X LUV plane, because in this case we find that 4 of our sources are lying well into the domain of X-ray weak AGN. And indeed, according to the definition by Pu et al. 2020, an AGN can be classified as X-ray weak when the difference between the observed value alpha X and the one expected from the given adopted alpha X LUV relation is smaller or equal than minus 0.3. Which translates into what they call a weakness factor, F weak, greater or equal than 6. And we find that a fraction of X-ray weak sources with F weak greater than 6 is the 30% of our sample, while being just the 6% of a much more representative sample of type 1 AGN analyzed by Pu. Not only that, consider that there is not a one-to-one correspondence between these 4 sources and the previous ones, because only 2 of these do also have a somewhat shallower value of gamma. And we find that their X-ray weakness seems to be intrinsic and not due to absorption along the line of sight to the nucleus. Another interesting thing comes because this fraction of weak sources is similar to those found by both Nardini et al. In 2019 and Zappacosta et al. In 2020, but there is a main difference here because their samples mainly comprise hyperluminous quasars at high redshift, around 2 or 3. That's much higher than that of our sources. And all of these may point towards 2 indications. The first one is that maybe we may not need to go that deep with redshift to recover a similar fraction of X-ray weak sources. And the second is that probably a high Eddington ratio might favor some accretion disk conditions that enhance the probability to catch an AGN in an X-ray weak state. We were also awarded time with Swift to monitor these 4 X-ray weak sources. 3 of them have been monitored so far. And as you can see, the first 2 are still lying in a weak regime. And for the first one, it's true, we do not know what happened in the intermediate gaps between 2011 and 2018 and 2018 and 2021, but there might be at least a possibility that this source has been in a low flux state for almost a decade. While the third one, J1103 plus 41, has awakened, and last year its X-ray flux was larger by a factor of 7 with respect to the previous XMM observation, and as of January of this year, we still find this source to be in a high flux state. But all of this is not enough. We need more data, and that's why we're currently working on the analysis of public archival data of serendipitous Eddington AGN, with the goals of investigating their X-ray spectral and variability properties, the presence of outflows, their incidence, their characteristics, and eventually to probe different physical scenarios to account for the observed variations. And in order to do that, we perform a cross-match between the latest release of the XMM serendipitous source catalog and the catalog of spectral properties of quasars from the SLO and the XIV. In the cross-match, we select only radio-quiet AGN. We require that each source must have at least one good quality observation in terms of the photon counts in the broad API band. And we select only, of course, sources with a sufficiently high value of lambda Eddington, which we set to 0.6. And the black hole mass estimates are only coming from Balmer beta or magnesium second, to avoid all those issues related to the carbon-4 estimates. And in the end, we obtain a catalog that we called XMM Newton High Eddington Serendipitous AGN Sample, or XS. Now, XS contains 161 observations of 6 to 9 AGN, 25 of which can rely on multiple observations. And the whole sample covers large intervals in terms of parameters such as redshift, bolometric luminosity, black hole mass, and Eddington ratio. And I'd like you to notice that the multi-epoch subsample of XS is well representative of the whole sample in terms of these parameters. Now, XS proved to be promising since from the start, given that the first source we analyzed, PG1448 plus 273, had a UFO in its spectrum that we could analyze thanks to WINE, that's the novel model photonization code developed by my colleague Alfredo Luminari, who presented this before. And what's also interesting about this source is that it has 20 Swift observations, the blue points over there. And we find that after the UFO has been detected in the 2017 XMM Newton observation, the value of FOX drops abruptly, landing into the domain of X-ray weak AGN, to recover to the previous state after a few months. And this might indicate a connection between the presence of the UFO and the weakness we observe, given that maybe such a powerful disk wind can subtract a large fraction of the accreting material in the innermost regions of the disk, reducing the flux of seed photons directed towards the corona. What we're seeing in these days is that also other XS AGN are interesting. Consider this. This is an AGN at redshift 1.3 hosting a 10 to the 9, sort of mass black hole. And for this source, we find both soft and hard flux variations up to a factor greater than 2 in approximately 1 week in the rest frame. And that was totally unexpected for an AGN hosting such a massive black hole. The next one is even more extreme if we want. This is an AGN at redshift 0.7 with a 10 to the 8 solar mass black holes. And in this case, we find flux variations up to a factor of 4 in approximately 2 weeks in the rest frame. And the next one is also interesting because this source is an AGN at redshift 2 hosting a 10 to the 9 solar mass black hole, and we find it's always being observed, as you can see over there, in a low flux state. Now, very preliminary results from the analysis of the longest observation of each of the 25 multi-epoch XS AGN, the blue points, seem to be in agreement with our previous work, with what we found in our previous work in terms of the large scatter, in terms of gamma, in the gamma Eddington plane. And once again, we'd better be very careful when using this kind of relation to estimate the black hole mass. So what we're seeing in these days is that XS AGN can show considerable spectral and flux variations over different time scales from a few days up to several years. So what we're going to do eventually is to try to understand what's the reason behind and what's the physical process behind all of these variations, including those of derived quantities such as the X-ray bolometric correction and delta X, given that the vast majority of the sample, almost the 70%, has simultaneous optical data from the latest release of the Serendipitous OM catalog. But as you can imagine, this is a very preliminary stage, so I'm really open to any suggestion from all of you. And I think that's all, and thank you for your attention.
Thank you, Marco. Very exciting work. And I was wondering, do you have in your sample some of these super Eddington maybe objects which are accreting with super Eddington rates? And if so, are they also? Do you find them also X-ray weak?
Well, okay. As I said before, regarding the XS sample, we also have AGN which are super Eddington, but I haven't analyzed them, so I really can't tell it. For the previous sample, those of the 14 AGN, Also those sources that are X-ray weak, maybe they are not super Eddington, but they're very close to the Eddington limit. I mean, like 0.96, something like that.
Any other quick question? I have one. One of the sources seemed to have been reactivated in the Swift monitoring. It was very low. And what's happening in the optical? Do you know at the same times?
Do you mean the UWAT data?
Yeah.
Well, I'm not really sure about it, but as far as I remember, there is not a variation, a strong variation in the optical. I mean, the major variation is in terms of the X-rays. I mean, we have this huge factor of 7 that is not witnessed in the optical. I mean, there is a much smaller variation over there.
Okay, thanks.
Thank you.
So, let's thank Marco again. Next speaker is Luigi Pachani. The microphone is there. He will tell us about waiting times between gamma ray flares of flat spectrum radio quasars and constraints on emission models.
Hello, everybody. Waiting time here are defined simply as the time between consecutive flare of gamma rays that can be usually found with light curve strategies. So you decide a bin and make your light curves. Here I decided a different strategy, that is I used clustering law and then applied the scan statistics to build a set of clusters that is statistically relevant. Oops. Ci riusciamo? Che è successo? Okay. There is a parameter here that is the threshold. That is, if you work in time domain, is the inverse of the rate. If, like in this case, you work in exposure domain, is the inverse of a flux threshold. That parameter is scanned on all possible values when you construct your clusters. And at the end, you have a tree of clusters. Okay? The method, of course, has a sensitivity that unfortunately differ depending on the source flux during the whole period, and also has a resolving power. Too close flares cannot be resolved and are pile-upped. Okay, and this is the case for TC454. The tree is simply a light curve that is called unbinned because there is no binning, it's a clustering strategy. So you can define the root and the leaf. And for each, as far as you speak about the tree, you can distinguish between parent and descendant in all the tree. Okay. It's a photometric method, so sometimes you get flaring activity from nearby sources, or like in this case, a solar flare. What is interesting here is that on account of the fact that it is unbinned, you're able to distinguish also activity of lasting about 7 minutes, and in the same representation, you have also flare lasting several 10 of days. Okay, this is the case for another source. And this is the sample selection. Okay, I use the third Fermi catalog. I only use relatively bright source with TS larger than 49 and remove the case where sources are too close to the galactic plane to avoid some confusion. Then, due to the fact that it's a photometric method, peak flux obtained with the photometry and is compared with the flux obtained with the livelihood to discriminate spurious flare from nearby sources. Okay. I also performed a lot of simulation with time series, taking into account the exposure of each sources, and it was possible because the method is extremely fast. The multiplicity of the problem is proportional to the number of photons in your time series, while other methods are really slow because the multiplicity is proportional to the number of events to the square. Okay, and this is the sample of waiting time. I use the representation on the left that is a little bit peculiar. It is in logarithmic scale, and is the number of beams divided by the beam width. In this case, if you have a Poissonian process, on the short time part, you have a straight line. And this is the function used to make the best fit of that distribution. There is a set of bursts of flares. So within each burst, you have a number of flares. They are distributed uniformly along the burst. This is the Poissonian part. And the bursts are distributed uniformly during the observing window. So you can find a typical burst duration of 0.6 year and a burst rate of 1.3 per year. Of course, you have also another component there that is a fast component that acts for time that are shorter than 1 day, but is roughly defined with the sample that we have. Really, you could also fit the model assuming that somewhere there is a pole. In this case, the distribution of waiting time for short waiting time rises and partially compensated the fast component. But if you account for two components, the two models are statistically indistinguishable. Okay, and this is the same distribution with the same parameter dividing the sample in slices and for single sources. These are the brightest sources, so sometimes you are able to distinguish close flares. Okay, the case of CTA is peculiar. There is also some case for 3C454 and for 3C279. While in the other case, the statistics doesn't allow you to distinguish close flares, and you lose the component for short waiting times. CTA is peculiar because all these flares happens during two periods that were associated in radio with the crossing time of moving future through standing future of the jet. These are the sample of some other source for some other source, and you see that you have a lack of events. If you exclude the CTA from the sample, you have a completely Poissonian process, but I suspect that this is the result of the lack of events due to pile-up and the case where you are able to distinguish this event from the fast component. So we cannot safely say that this is only distribution coming from only one population for times shorter than 1 day. This is what happened in radio. I'm trying here to compare with similar time scale. We have seen that we have only two time scales, essentially. A fast component active for times that are shorter than 1 day, the bursting period, the time, typical time that is 0.6 years, and then the burst rate. So this is what we have in radio. you have to say that it's an apparent distribution, if you want, because it includes only the flares that are the denote that are resolved. So the number of flares could be larger. It is a little bit strange because this is 3C279. In some cases, you usually find that the sources fade with a typical time scale, so they fade exponentially. And for the case of the knot C31, you observe an almost flat distribution. This knot is accelerating. You see that there is a parabola there. But we expect that this knot fades quickly during the path because the magnetic field decreases with 1/d. And this does not happen, maybe because, there is some acceleration along the path. This is the comparison with radio of the gamma ray sample, and they are compatible, at least for the brightest sources. And in optical, we see something similar regarding the short waiting time. These are observations with the TESS that works in optical. And you see that there is a white component emerging for time shorter than 1 hour. The sample was defined for the waiting time, but you clearly have also the luminosity and the duration. It is limited, it's a flux limited sample. And this is the distribution in white for the sample and in yellow for the simulation, taking into account the Doppler factor and cooling effects. So they are quite close, but I have to refine this. But you can use this to study the same waiting time distribution, taking into account the exposure. So if you simulate a uniform distribution, you obtain a rather different profile. It's obvious, but if your exposure varies too much, you expect that the waiting time distribution to be changed. This does not happen. And instead, when you apply the burst scheme, you still obtain the true distribution, with the exception of the short time range, where obviously you lose the events due to pile-up. Okay, you can assume that the flare come from recolimation shock as proposed for CTI 102, but you have to assume that in this case the knot comes in a train that is long about 2 parsec along the jet to justify the burst duration. Or you can assume that the flares are emitted along their path. In this case, the path is about 30 or 50 parsec, but you expect that the flares are extremely weak at the end of the path, toward the end of the path. This could be maybe compensated, assuming that the knot accelerate during the travel. Alternatively, you can assume that all that you are observing comes from reconnection, where the fast component comes from the plasmoid production, and that the burst rate and burst duration are due to, or by the fact that that the magnetic instability lasts for some time and have a certain rate, or that the plasma injection is sporadic. Okay, I finished.
Questions for Luigi?
Just a curiosity. So you select the sample out of the 3FGL, right? And then you took all the events for the analysis of the light curve. Did you take into account of the, let's say, observing strategy of Fermi? No, they change. At the beginning was uniform, then they.
Yes, I take into account not exactly, because sometimes you have there was some pointing. I take into account adopting the real exposure of data. That is not exactly the same because because sometimes the observatory reacts to a particularly bright state of the source, like for TC454. But these cases are not too much, probably.
No, it was just
fine-tuning
in the threshold, for example, when you are looking for the specific flare or.
No, the threshold is varied from, let's say, 10 to minus 9 to 10 to the minus 2. You get everything.
Okay. Thanks. So while Giorgio comes to the stage, I have a very silly one. Do we have enough time resolution to understand if also the flares are spiky or no?
What do you mean for? Maybe yes.
So every burst is made of several flares. So
yes.
Are these smooth or we have enough time resolution to understand if also the flares have a spiky structure?
Only in I didn't show you exactly these cases that are for CTA 102. They're on my paper and also in Dammando that make these studies, where you are able to resolve these spikes. And so there you find that sometimes the spikes are very close. And in all the other cases, you essentially are not able. So in my opinion, you have not the statistics. That doesn't mean that the substructure is there, okay? And the other case was TC454, that it was the 2011 period of activity, where the activity the source was very bright, and the Fermi collaboration, for example, was able to make the fit with 4 or 5 single flaring episodes. But the subdivision, I try not to avoid to use fitting there, because maybe what you use to fit is the result, not the a priori distribution. And maybe this is the case for CTA 102. You observe that very far from the flare, the flare flux, you see the source that is increasing, and then to decrease. But if you interpret this, for example, as a peculiar jet where you have a region that is the region where you have the knot that is pointed toward the observer, and this explains the knot, for example, because when you observe this particle and they are pointed toward you, you see a bright feature. So when you're approaching this knot, the luminosity increases dramatically from very far. So this is the result of the activity. It's not the a priori distribution.
Okay, thanks. Let's thank Luigi again. The next speaker, Giorgio Lanzuisi, nuclear and large-scale outflows in IRAS F1111-9.
Okay, I hope you can hear me. I'm going to present new results on mainly the nuclear outflow in IRAS 1111-9. This is maybe the name doesn't tell you much, but this is quite a famous and important source in the framework of AGN feedback and AGN galaxy coevolution. It started this career as a rather normal, I would say, galaxy merge at redshift almost 0.2, hosting a ULIRG, a very powerful QSO, accreting almost at Eddington limit. And it was shown in 2013 to have a pretty strong molecular outflow in OH, seen with axial packs, velocities up to 1,000 kilometers per second. But this is, again, it's a remarkable source, but it's quite a common feature. Actually, 60% of the sources in the sample of that paper showed similar outflows. It became more famous and made the Nature cover in 2015 when it was discovered the strong disk wind in a deep Suzaku observation. You can see here the spectrum and the residual where you can actually see this very evident absorption draft. So it's what we call also ultra-fast outflows. Velocity is a fraction of c, and pretty large mass outflow rates and momentum fluxes or kinetic energies. Very wide turbulent velocity to fit this very wide absorption. And but the reason why it made the Nature cover with this rather misunderstandable artistic impression was that it was the first time in which we could link the nuclear and the large-scale outflows in terms of energetics. So you see the red stars are IRAF 11, 11, 9, both in the nuclear outflow and the large-scale outflows. All the other sources are either have one or the other one. In this case, the energetics were consistent with an outflow that is energy-driven. So basically, the wind gas doesn't have time to cool and expands in the ISM, inflating a bubble, and then the large-scale outflows has a power that is boosted by basically the difference in velocity. There were quite a series of follow-up papers on these outflows. This is particularly interesting because in this table you see different estimates of the energetics of the outflows, both in the OH and CO that was observed with ALMA in this paper. And you can see that you can get very different results depending on the assumption that you make, the parameter that you use. So this is just to point out that things are not that simple. There was a confirmation of the X-ray wind, disk wind from a NuSTAR observation in 2017. And then this source ended up in a paper by Emanuele, where they were comparing with the Markarian 231. And you can see that here that they basically end up with the opposite conclusion. And the main reasons are that there is a different estimate of the large-scale outflows where you average over the flow time instead of considering the local value. And also there was a big difference in the wind power based mostly due to recomputation of the black hole mass. So you can see that the situation is quite not so clear, and in the recent years we have populated this plot with many more sources, and we don't have still a clear picture on this kind of connections between nuclear and large-scale outflows. And by the way, I also discovered that there was also published a radio jet, compact radio jet with velocities of almost 0.6 c. So back in 2019, when we were collecting the sample for the Subways large project that Gabriele presented yesterday, we realized that actually IRASF 11.11.9 was the brightest one source in this range of redshift and luminosity that didn't have a deep XMM observation for high-quality spectroscopy. And by the way, I encourage you to see also the poster by Pietro Baldini on Tomas 0918. That is another source that is in the same range of redshift and luminosities of the Subway sample, but got observed in a different project. So this sample is getting larger and larger as we collect new data. So we asked and actually got a deep observation with XMM in November 2021, simultaneous with NuSTAR. I will skip all the part on the data reduction, but we used all the updated and tested best practices that Gabriele developed and for the work on Subways. And what you end up with is this spectrum that is, you can fit it with a power law, with a rather steep photon index, 2.4. And both cold and warm absorption, but the most interesting part is, of course, the residuals that you see here to this fit. There is emission and absorption at around 1 kV, emission where you expect the iron K line, and negative residuals above that. So we can zoom on these regions. Here is even more evident. There is this emission and absorption profile in the soft band. Where you expect to find the iron K line, there are actually two lines at 6 and 7 kV, and two quite strong absorption features at 9 and 10. You can run a blind search on these energies, basically scanning the energy and normalization, and you end up with these contours. The red ones are for 4 sigma significance, and you can see the energies that are measured for the emission and absorption. So we actually have 2 very significant absorption features at 9 and 10. This one seems also to be kind of resolved. So one thing to notice is that these are the same residuals, but I split at PN and MOS, so this is more clear. These features are at an energy that is too far away to be K alpha and K beta resolved lines. This is an example. It's not a fit. It's just one example of what you will expect from a photoionized gas, high column and high ionization parameter. But they are too nearby to be the result of the blending of these 2 pairs of lines. So basically, there is no way with these simple models to fit both features with one single absorber. And the same is true also for the soft component, because you cannot fit that the one around 1 kV and this higher energy feature with the same absorbing model, because the ionization parameter would be very different. So very long story short, I ended up fitting all these different residuals with actually 3 absorbers. One is called absorber 1, 2, and 3. One with low energy and column density and ionization parameter to fit the soft part, basically, and 2 different high column, high ionization for the features at higher energy. And we also modeled the emission with 3 Gaussian for the moment. So the parameters of these absorbers, this is the warm absorber that is always there, but the parameters of these absorbers are shown in this table. Basically, you have 2 high column, high ionization parameters and 1 low column and low ionization parameter, but the velocities are all pretty high and consistent within the areas within each other, more or less. And so if you look at the distribution of these parameters in a plot that I borrowed from Roberto's papers of 2019, here you have the standard warm absorbers. Here will be the locus of UFOs, so in terms of column density, high column densities, and outflowing velocity, very high outflowing velocities. And here is ionization parameter versus outflowing velocity. So again, the UFOs are here, the warm absorbers are here. And in this paper, they were reporting a series of measurements of what they called entrained UFO, so high velocities, but more similar to a warm absorber, so low column and low ionization parameters. These magenta points are some other measurements from the literature, and this is where the absorber 1 ends up. So we can now put different names to these absorbers. I would call it entrained UFO. It's more or less in the same region. It's more, in terms of ionization parameter, it's more similar to what was observed, for example, in PDS 456, based also on RGS data. For our source, the RGS data, we just looked into that with the help of Gabriele, but the source is too faint. It's also obscured. And then the 2 UFOs are here. They are actually reaching the limit of where our absorbing models are defined. So this is the scheme that was published in Roberto's paper. Basically, you are measuring the UFOs here nearby the launching radius, high columns and high ionization parameters, and then this expands and the density decreases, and then at some point there are these clouds of lower density with respect to the UFO here, but of course larger densities where they live, and they are pushed through instabilities, and they can reach the same velocity of the UFO and then end up being the warm absorber at much slower velocities. In our case, the warm absorber has a limit on the velocity, but is consistent with 0 basically. Right. So in the end, you end up with this pretty complex model. We have features, absorption features from the UFOs, mostly in the soft, and a series of features in the hard band. Interestingly, the silicon and sulfur lines actually do fit some feature that is visible in the spectrum around 2 and 3 keV. So the fit is not only anchored to these fits, but it's actually reproducing wiggles in the spectrum also at different energies. And you see the warm absorber here and the emission lines. This is actually very similar to what was observed, as I said, in PDS 456 in this paper by Reeves. They had the RGS data, so the resolution is much higher, but basically it's a blend of, in our case, it's a blend of iron and neon and several excitation levels around these energies. I also tried to derive a covering factor from this spectrum. Since we have emission lines, you can try to fit those emission features with the same photoionized gas that is doing the absorption, but in emission. And then basically from the normalization is the same approach that was used by Emanuele in PDS 456. You can derive covering factors. They are very large, as it was in the old Suzaku and Nustar data. Interestingly, to fit the emission here in the soft, the UFO, entrained UFO, must be beyond the warm absorber, otherwise it will be absorbed and there is no way to fit this without overproducing flux in the hard band, or medium band. I have also a couple of slides on variability, since I ended up in the variability session, probably because I mentioned variability in the abstract. So we observe variability in the light curve. This is the full band light curve, and it was just a quick test we did at the beginning, was to divide produce spectra for the high and low state. They're simply divided on count rates, and you end up with two very similar spectrum. This is just PN, showing also the background. But if you zoom in on the absorption features, it seems that there is a difference, at least in one of the two features. The low energy one is the only one that in the low state is consistent with not being there. It's consistent with 0. Of course, this has to be treated a bit carefully, because the significance of this line will change with the flux that you have in the two spectra. So summarizing, we found a powerful disk wind in IRSF 11.11.9. Well, we knew that was there, most probably, but we resolved it into components for the UFOs, and also found for the first time the entrained UFO. Actually, it looks like that is even visible in the old Suzaku data at 1 keV. I mentioned energetics, but in the end, I didn't bother computing energetics for the winds, because, well, for the UFOs, given the parameters of the UFO, you will get similar values to the one published in 2015 and 17. But as also Alfredo was mentioning this morning, there are huge uncertainties and assumptions that you have to make. And so I thought it was not really useful. Instead, my hope is that with good quality, good quality spectra, we can try to fit more physically motivated model, as Alfredo was mentioning. We have Wine and Disk Wind in the team, experts in the team, so to try to reduce the uncertainties and the assumptions that go into this computation. And regarding variability, we have to test more carefully what happened inside the XMM observation and on long time scales. And I will stop here.
Thank you, Giorgio. Questions?
Thank you. Just have a curiosity on the emission side. If the fit of the emission component has the same parameters as the corresponding absorption, or you also allowed for a freedom for example, ionization parameter, turbulent velocity, or column density?
No. The parameters in column density, ionization, and turbulent velocities are the sing. The position, the outflow velocities is different and typically consistent with 0, slightly outflowing. But yes, they are basically the same tables used in absorption and emission. C'è Roberto là dietro.
You are too far, Roberto. Quickly.
Now, do you have Muse or iView of some sort?
No, not that I know of. We didn't do anything in the multi-wavelength side, and actually we have also to go back to the optical spectrum to look better at the estimates of the mass. So no, I think there is no such data, but we can propose.
That would be very interesting, in my opinion.
Let's thank Giorgio. You can discuss this later. Next speaker is Cristiana Spingola, the radio VLBI view of the outstanding gamma ray flare of the lens Blazar PKS 1830.
Thank you. So, first of all, I would like to thank the organizers for giving me the opportunity to talk about what I've been doing at the Institute for Radio Astronomy in Bologna. So, I will talk about the radio follow-up of the outstanding gamma ray flare that you see on the top left here with the white dots of this beautiful lensing system, which is PKS 1830. It's on the right, 2 lensed images and an eye-sized ring. So we know that there is an evidence for a connection between the radio and the gamma ray emissions in blazars. And blazars, they are the dominant population of the extragalactic gamma ray sky. So this evidence comes from statistical studies like flux correlation. You see this on the right. So we plot, if we plot the flux at the gamma rays against the flux density at the radio wavelengths, we see correlations from the very low frequencies like 150 megahertz up to the very high frequencies. At the same time, there is a correlated variability between the radio and the gamma rays, and this is shown on the left. So we see when we observe a gamma ray flare, there is often a radio counterpart of it. So it seems very natural to think that there must be some common emission mechanism, or at least the underlying emission mechanisms must be connected. However, it's not that easy, because very often, actually, there are orphan gamma ray flares, so we do not see any radio counterpart for it. And this has been interpreted as the gamma ray flare happening in the very innermost region of the AGN, like within the broad light region, and so that is an optically thick region to the radio wavelengths. Sometimes you observe at the radio wavelengths knots, so shocks moving around the jet. Sometimes there aren't. And the most puzzling part is that not all blazars have been detected at gamma rays, so why is that? So instead, when we do observe a radio-delayed flare with respect to the gamma ray, this means that the gamma ray emission originates along the jet. And the just simple causality arguments from the gamma ray variability imply very compact regions for the gamma ray emission, so parsec or sub-parsecs in size. So this means that it would be really useful to have high angular resolution observations at gamma rays and radio wavelengths to connect the relative emission, the relative location of these two emission regions. So at the radio wavelengths, it's quite easy to achieve high angular resolution. We have heard about the EHT yesterday. That's at a different level of the term high angular resolution. But typically, we can obtain angular resolution between milliarc second and even sub-milliarc seconds at the highest frequencies. On the right, you see the very longest line array, which is based in the US, and that's 10 antennas connected, linked together, acting as a single telescope. However, at the gamma rays, we are not that lucky, and the angular resolution of the Fermi-LAT is only of a few degrees. But the Fermi-Large Area Telescope has a very nice time, very high time resolution, so we can take advantage of that and boost the spatial resolution by using strong gravitational lensing, and in particular, one of its most striking and primary manifestations, which are time delays. So if we have a background source like a blazar that is variable, and between us and this background source there is a concentration of mass, for instance a galaxy, then the light coming from this blazar is deflected and magnified into multiple images of the same source. So any variability coming from this source will appear at different time in the two lensed images, and this is simply because of the different path length of the light rays. So what you see in this video is what Fermi observes, so a single unresolved light curve, which is a pulsating signal that is the sum of the underlying lensed images. In this case, there are two, but you see on the top right there can also be 4 or many more. So time delays are super powerful probe for dark energy because they provide a one-step measurement for H0. However, we can also use them to constrain the relative location between the radio and the gamma ray emitting region. And this is because any difference between the gravitational time delay measured at the radio and the gravitational time delay measured at the gamma rays directly implies that the two regions are spatially separated without even performing any lens mass modeling. So we only know two lensing systems that are gamma ray loud, and they are both blazars. One is BO218, which you have seen in this movie, and the other is PKS 1830, where we have two lensed images, this nice ring-like emission that is due to the steepest part of the compact radio jet, but it's distorted into a nice tail ring. So it's a very well-known lensed blazar at redshift 2.5, and many time delay estimates have been already found in literature, so at the radio and gamma rays. You see here the values, but the point is that some of these values are not consistent among each other. So one may think that the two emitting regions are separated, but the data are not simultaneous. So these time delays have been measured at very different times in the life of this blazar, so with different light curves. And so it's not really that trivial to say that these two regions are not connected, or they are connected. So we really need multi-band simultaneous observations of gamma ray flaring blazars, lensed blazars, to understand the connection of the radio and the gamma rays in these powerful events. So PKS 1830 gave us another opportunity to try this method because in April 2019 showed its most bright gamma ray flare that you see on the right. Actually, that was the brightest event detected by the Fermi-LAT in the last years. And so during this event, we followed this up with a VLBA right on top of the brightest part of the flare. So we followed this up for about 3 months at 3 different frequencies with the aim of finding any morphological variation, but most important to determining the the radio gravitational time delays from spatially resolved light curves. So now I'm going to show you very boring VLBI images because we did not find any knot during this period of time. And the lensed images are resolved at 15, 24, and 43 gigahertz. So here we are going at very high angular resolution with a beam size of about 0.5 times 0.2 milliarc seconds. And 0.2 milliarc seconds at redshift 2.5 corresponds to about 1 parsec. So it's very high angular resolution. So we had the most densely sampled light curve at 43 gigahertz. I'm showing you here where I'm showing you the two light curves from the lensed image A in white and the lensed image B in red. You see that there is significant variability in this period of time, and we use the cross correlation and the chi-square method to optimize for both the time delay but also the magnification ratio between the lensed images. And what we find, here you see the shifted light curve, that the best value is of about 28 days. So the magnification ratio is of about 1, so this means that pretty much the two images have same magnification, which was kind of expected. So we have actually a very good precision on this time delay because of the spatially resolved light curves, but also because the light curve was very densely sampled. And recently, actually, we could compare our time delay with a very precise lens mass model coming from Mueller 2020. They followed up this flare with ALMA, and in a similar period to our VLBI follow-up, and they detected the central image. So all the lensing systems should actually show an odd number of images, but the central image is the most difficult and challenging to detect because it's mostly magnified. So this flare enhanced the emission from all the 3 images, and this gave the opportunity to revise the lens mass model and give new predictions. So our value is in very good agreement with their prediction. But we also had access to a very long time monitoring with the single dish data from the Owens Valley Radio Telescope. The angular resolution is of about 2.6 arc minute, but the time baseline is of about tens of years. So you see this light curve on the left, and we use the same method that it has been used at gamma rays, so the autocorrelation function, to determine the time delay, or at least a delayed version of the same signal in this light curve. But what we found is actually two peaks in the autocorrelation function, one centered at 29 days and the other at 34 days. And this is exciting because it's the first tentative detection of the time delay with the central image. And it's, again, in good agreement with the prediction of Mueller, which is reassuring. So to conclude, our new measurement for the time delay in PKS 1830 is precise, more precise than before, and this gives us really the opportunity to compare this with the gamma ray gravitational time delay. The analysis of the Fermi-Lat data is ongoing by Sarah Buson, and so stay tuned for the comparison between the two time delays. But currently it seems that there is an apparent discrepancy with the previous gamma ray estimates. You see this on the plot on the left. But we cannot really compare our data with previous time delays estimates because they come from different gamma ray flares. So they might be uncorrelated, and that will be okay. So, and finally, we only know two lensed blazars. So any conclusion that we can achieve with these two systems cannot really be extrapolated to the entire population. But the SKA and SKA VLBI are predicted to find 10 to the 5 lensing system, and among them there will be thousands of lensed blazars. So the future is bright for this kind of application. Thank you.
Diana, any questions?
Could you? I didn't get the dimension of the region you showed with ALMA. How large was the region you identified?
You mean the field of view?
Yes.
So let me check. So the angular resolution is about 60 milliarc seconds, so we are of about an arc second field of view. So keep in mind that the separation between A and B is of about 1 arc second.
Yeah. Yes, because the two images, A and B, are resolved by Chandra. I'm not sure about the C1, probably not, but A and B are resolved.
Yeah, it would be really interesting to actually compare it with the Chandra measurements. I saw that there are many data in the archive from many different times. I think they have been used for microlensing, but thanks.
Other questions? If not, let's thank Christiana again. Francesca Panessa will tell us about radio variability in radio quiet AGN.
Okay, thanks. Thanks the main organizer here. I also would like to thank the organizer of the meeting. And thanks to my frequented collaborators that have participated to all this work that I'm presenting. I would like to tell you that this research line started in one of the past AGN meetings in Montagnana back in 2006 when Gabriele Giovannini and Marcello approached me for work, to do some work on the radio for CIFER Galaxies. And so this research line was developed, and today I will try to show what radio emission can tell us for radio AGN, for AGN. So first of all, we all know that AGN with relativistic jets that are pointing toward us are dominating all the emission of the electromagnetic spectrum. And such emission is highly variable We know that we have observed strong variability at different frequencies. This variability is also showing, is pretty unknown. It shows flares and different time scales, so it's really strong. But we know that at least is the jet that is producing such variability. So when we come to radio quiet AGN, you might think that they are very boring in the radio because they are quiet, but this is not the truth. I'm talking about non-jetted AGN, and Paolo may be upset if I call them radio quiet, but we all call them radio quiet, so I will stick to this classification. But so radio quiet AGN, they're not boring in the radio. Once you remove the emission from the relativistic jet, they come out with very different, I mean, no, in radio quiet there is no jet. So what you see is that you can observe, depending on your source, low power jets, like low speed, low power jets, which looks like the potential relativistic jet. Or you can see outflow emission, which is less collimated, or star formation in the form of rings. And depending on your resolution with the radio, you can even resolve such emission and detect knots of these low power jets, or the shock regions of the outflow, or resolve better your star formation ring. So this is to show you that they're not boring at all, but you can do the physics using this wavelength. And this is what we have outlined as 4 main physical processes that you can witness with the radio emission, which is star formation, corona emission. The corona, which is producing the X-rays, may produce synchrotron emission that you observe in the radio. There you can observe winds in the radio because the shocks are producing synchrotron emission, or these low power jets, as I was mentioning. Most of the time, all these emission mechanisms are competing, are all together in the same source, and you will observe the most dominant, or you will have a hard life in trying to disentangle what is producing what. But you can use some of the observational evidences to try to discriminate which is the emitting source. So we move to the radio variability in radio quiet sources. All these different mechanisms may or not may be variable. For instance, we expect not to observe too much variability in a star formation region. But like for the other mechanism, we do expect some variability, although we don't know really what to expect because there have been very poor studies on the expected variability in the radio from this mechanism. But people in the past, like all these people here, have tried to do some work in this sense, like using single sources or very small samples. So these works are very, very preliminary. But they found that there is variability in the radio quiet, so 10, 20% nearly. And I'm showing you one example. This is NGC 7469, a local Cipher galaxy that Ranieri has monitored at 95 gigahertz, so quite high frequency. And he observed significant variability. The group observed significant variability. The source was also monitored simultaneously with SWIFT. And there is a tentative time lag of 14 days between the two light curves. And this is favoring the idea that the radio emission may be coming from the corona, from the hot corona that is producing X-rays. But we still have to explain why we observe 14 days, for instance, of time lags. It's very hard because you need, as it was said, as Barbara mentioned this morning, you need long sampling of your light curves. You need a very high cadence of sampling, so it's very hard to do this kind of studies, especially for radio quiet AGN. We did this experiment of observing this narrow line Seyfert-1, Mercurian 110, which is extremely radio quiet from the radio loudness parameter, with the VLBI, Christina was showing you before, the VLBI interferometer, at 5 gigahertz. This is the map. This is how it looks like, Mercurian, so boring, not unresolved point-like source. But we took this map every day for a few weeks. And it turned out that even if boring, this source is varying on daytime scales variability. And this is the first time that this experiment has been done on the spatial scale of milliarc seconds resolution, so very, very high resolution. This is a region of around 1 parsec. But since you can apply the causality argument for the day variability, so you say that the light curve, the speed of light is constant, so you can derive the region where the emission, the radio emission comes from. And it's for the black hole mass of this narrow line Seyfert-1, which is 5 to 10 to the 7, it's less than, because you can put only an upper limit, it's less than 180 Schwarzschild radii. So it's quite a very nuclear region that is producing such variability. Interestingly, like a few years ago, an XIV Newton observation showed that there was an energy-dependent delay. It was modeled with a comptonization of a hot plasma within 10 Schwarzschild radii. 10 and 180, they are not so different. So maybe again, this radio emission in this narrow line Seyfert-1 is produced by the same hot corona, or not. I mean, could be also the base of a jet, because the observational evidences of this source in the radio can also be explained with a low-power jet. So what we need is, of course, better sampling, although it's very hard to get light curves with the VLBI. Another source, it's very interesting. This time, this is a super Eddington, narrow line Seyfert-1, you may know it, which has shown very strong X-ray, flux, and spectral variability, and we've explained this variability as due to reflection or partial covering from low ionization material of around 100 Schwarzschild radii. And we had some speculation on the fact that it could be a clumpy disk wind. We monitor the source simultaneously with the radio, with ATCA, because the source is in the south, at 3 different frequencies, 5, 9, and 18 gigahertz. To my knowledge, also this is the first experiment for a source to look for variability at different radio frequencies in a radio quiet. And so, yes, we detected variability at 3 different frequencies, and the radio slope is also changing. We wonder if the different variability components here may come from different different components of low-power jet, for instance. This was reported as a radio loud source initially, but now we measure that it's a radio quiet, so I suggest this might be a class of changing look radio AGN. We like a lot this changing look stuff, so I'm going to use it. The last experiment we are conducting is on performing light curves with AMI at 15 gigahertz for a sample of hard X-ray selected AGN. We have the radio light curve, the optical light curve from the Zwicky factory, transient factory, and Swift. Swift simultaneous observation. We're working on this because it's quite hard, as you may understand, trying to cross-correlate different light curves. But it's interesting because all of them do vary, even if they are very low flux. And the variability fractions ranges from 10 to 60%. So they're quite variable. So I want to conclude by saying that these radio quiets, AGN, even though faint, they are of interest, and they show radio variability that can tell us better on the physical mechanism behind them, and they can use as a new tool to explore the physics, the underlying physics. And there are plenty of new classes that are coming out because of these variability studies. Changing look AGN at all frequencies, tidal disruption like AGN, and the flaring Seifert that are flaring. You can observe them from Zwicky factory. You look at the optical light curves, and there are normal Seifert that are flaring. So there is a lot of new interesting science that can be done, opening this variability tool. I leave you with announcement of our website. You can visit to check if you want to know what we're doing, and advertising some projects that are available for students if you're interested. Thesis project and enough postdoctoral fellowship are eventually out. So if you're interested, you can also apply with us. And thank you for your attention.
Questions for Francesca?
Thank you, Francesca, and it's really great that we still talk about this thing several AGN conferences later. That's fantastic. About this Super Eddington object that was radio loud and evolved to radio quiet. This kind of look change is very surprising, because I can quite easily accept that something that is radio quiet turns on and becomes radio loud. But the other way around should involve very long time scales, because for the high luminosity, the extended regions to fade away, it would take, I guess, more than a few years. And so I wonder if this is just a change in classification because something came up with the original data, or if there is really a change in radio emission. And in that case, so this is a highly accreting object, so I guess it's quite luminous in optical and X-rays. So to be radio loud, it really means that radio luminosity was like 10 to the 25, 26, how high?
Yes. The radio data were taken with one of these low resolution radio surveys. So sure, you have to account like for large scale emission. Anytime we do a better high resolution image, and you lose your extended flux, and then you reduce your flux. So I think there is a component that comes from that side. And about decreasing the radio luminosity, yes, I agree with you. It's hard to explain. So I don't have an answer now, but still we're working on this source. It would be interesting to see why. Yes.
We have to move on, so let's thank Francesca again. Now Maurizio Paolillo will tell us about the universal GN X-ray power spectrum.
Hello to everybody. It's a pleasure to be here. Since I'm in the SOC of usually all the AGN conference, since I proposed Naples, I never have the chance to speak, so I'm very happy that this time I have it. So I want to show you some result about the universal power spectrum of AGNs, and I will have an easy job because a lot of introduction has been already done by Barbara this morning. And we've seen several talks showing that AGN properties are remarkably similar. For instance, if you take the whole spectral distribution, you can see that the alpha over X is remarkably constant over redshift, that the spectral index of sources is remarkably constant. Of course, we've seen through this conference example of objects that deviate from these relations, and those, of course, are the most interesting objects, but overall the population seems fairly, regular. And the same is for the optical, spectra in which we recognize features, the iron line emission width, and so on. So what about timing, which is one of the difficult part to explore, especially at high redshift? So most of the time we show plots of luminosity versus variance to show how they behave, and it's very complicated to explain to people why this shows that the variability properties are relatively constant. So we did an effort in the last few years to try to demonstrate if this variability is constant as the other intrinsic property of the AGN. So we've already seen this morning that the power spectrum of an AGN usually is modeled by a broken or bending power law. And I want to recall your attention on these parameters. This is the low frequency slope, this beta here. This is the high frequency slope, and the break frequency that Barbara was talking about this morning, which is the thing that we are going to investigate. And usually these are assumed to be, -1, -2, which is some average values. While the break can depend on physical parameters, and in part also the normalization of this curve. So we expect this because, as Barbara shown this morning, the time scale, dynamical time scales, thermal time scale, viscous time scale, or all of them to some extent will depend especially on the black hole mass, and then possibly through other parameters, for instance the disk height, can also include the dependence on the accretion rate. So this is not very, physically clear how this is linked to the variability, but, there are good arguments to expect this correlation. And in fact, Barbara showed that in local AGNs, we do see this trend. We see these power spectra changing with the black hole mass, and this is the famous McCarty plot in which going down from binaries to AGN, even including radio loud AGN, although that's a bit of a stretch, we have this relation in which this break time scale scales like the black hole mass and the bolometric luminosity of the sources. So now the point is what can we do at high redshift? I have to do it like this. No, wait. It's jumping 2 slides at once. Wait, can you go one? Yes, perfect. So in deep surveys, to go at high redshift, we have to use deep surveys. And deep surveys like this is the collage of the Chandra Deep Field South, as it's slowly assembled over almost 20 years, in which you slowly assemble the whole coverage. And here you can see sources popping out from the noise. And you slowly observe fainter and fainter source, and this is great for population studies. But this has, of course, also, a timing aspect that we can exploit here. So how do we do that? At high redshift and in this deep survey, we don't have such well-sampled light curves. So the problem is, what are we observing? So assume that you have a PSD spectrum, this is what we're assuming, with a form of this kind. This is just a bending power law with a typical break. It's just not a hard break forced in. And you can assume that this break scales like the black hole mass to some power, with some free parameter, which is the normalization of the power spectrum, the dependence of the break from the mass, and also the slope of the high frequency slope of this power spectrum. In this model, the low frequency slope is fixed to -1, but that can be changed as well. Now, if instead of computing this, you compute the variance of the light curve, the variance is to some extent the integral of this power spectrum. To some extent, because of course there are biases depending on the sampling pattern. And so you will get a relation like this, and this is what is shown here. And the interesting part is that this variance frequency plot, what we call the VFP, it actually shows features that are typical of the PSD. So you again see a break, you see a flattening and a steepening, and all this depends on the parameter on the PSD. So this is much easier to measure directly in these deep surveys. So in, for instance, in the Chandra Deep Field South, you can clearly see when you do, you observe epoch by epoch, how these sources vary and how they switch on and off. And looking, source relative to one another, you can see that the variability is actually real, because there can be some noise in the outskirts, but it's there. And in fact, the light curve looks like that. These, of course, are the best examples, and this is over 20 years. And so in here, you have different time scale that you can probe at the same times. And so we started working on this different time scale just on the Chandra Deep Field South a few years back, but now we're trying to push this using only time scale that are completely independent from each other, so that we don't introduce correlation in this. Now, this is just one sample, the deepest one that we have, but to try to see if all AGNs behave the same way, we started putting together what we could find in the literature. And the other obvious choice is the Cosmos field, with the work done by Giorgio back in 2014, in which, of course, this sample has a much sparser coverage than the fantastic coverage of the Chandra Deep Field South, but has a much larger area and much better measured black hole masses. And so they already show that there is an anti-correlation with black hole masses, although with large scatter, maybe not with accretion rate, that's still debated. And so this is another sample to include that. So we put together these two samples at high redshift, Chandra Deep Field South and Cosmos, and then we decided to include also nearby samples to sample the high frequency part. So we have object from the ASCA Tartarus sample and XMM Kaisha surveys that we heard about today. We have some light curve coming from RXT plus WIFT to sample the 10 days time scale, which are intermediate. We have sources of RXT, they've been sampled on 14 years time scale, so very long time scale. And then we have these two, the Chandra Deep Field South, a robust sample, and a Cosmos robust sample. Each one of these has different properties. This is the redshift distribution of the two high redshift samples here. So when you put all this together, what we did, we plotted mass versus variance plots for each one of these samples. And here you can see, of course, with a huge scatter, especially in the Chandra Deep Field South, we know that part of the scatter is due to the intrinsic stochastic nature of the source. Despite what you do, you will always have a very large scatter. And then there are problems in measuring the masses, especially in the Chandra Deep Field South. Also in the Cosmos, you see the same type of scatter. But overall, what you expect in the variance from the model is these curves that I'm showing, these curved curves. Although we tend to use linear fits over the fitted range to make the estimate more robust, and estimate the slope of these curves and the amplitude around 10 to the 8 solar masses. So these are the two Chandra Deep Field South and Cosmos sample, and then you can look what happens with the better sample nearby object, in which the source are even better on this relation on half a day, 1 day time scale. And then we have the SWIFT, which is 10 time scale. I forgot to put the label here. And there is the RXT, which instead are on very long time scale. And in fact, what you expect is basically no dependence on the mass, because you're probing the flat part of the power spectrum. So what the result is when you put all this together is this one. So in this plot, you see the frequency, and here you see the amplitude variability, and this is the slope of the mass variance relations. So each point here is one of these samples. These are the high redshift samples. These are low redshift samples. And I put here an example model, although actually we compare each sample with these yellow symbols, because for each sample we have the problem that Each sample is measured on a maximum time scale, but also minimum time scale. So you have to take into account the gaps in the light curve, the shortest time scale and the longest time scale of beam sample, and the biases due to the gaps. So actually, the estimate is between each point and the open symbols. But overall, basically, this is the trend that you expect, except for the RXT that are been on 300-day time scale, so you don't have the contribution of the fast variability, so this is why their model drops very fast. And you can see that the points are remarkably close to the expectation from the model, both in amplitude and in slope. And this is remarkable when you consider that we're spanning 3 orders of magnitude in black hole mass, 6 orders of magnitude in X-ray luminosity, and a factor of 3 in redshift. And this is done with one model. So if you look at the parameters that are coming out from this, what you get as a result is that you have an amplitude of this power spectrum that it's in agreement with what was found in the literature so far for nearby AGN. This fits also the high redshift sample. You have a low frequency band of around 3 days. And I remind you, this is for a 10 to the 8 solar mass black hole because it's where we normalize the radiation, but of course it can be rescaled for all the other black hole masses through the model. So it actually includes all the black hole masses. And the high frequency slope are actually steeper than what usually assumed. It's closer to 2.5, which is also what's been found in the local XMM AGN samples. So what the final result of of this work is that we are showing that actually the power spectrum is rather universal. There may be some dependence on the accretion rate, but from this data it's very hard to probe it so far, so you need more data. And what surprised me when I worked on this is that even very sparse sample like the Cosmos one, in which we take sources with even only 3 observations, can give you a good fit to this relation, as long as you have a large sample. So just to tell you that in the future, we're now already having Eurosita data. We hope that at some point the survey will be completed, and in the polls there will be multiple observation of nearby sources. Object like EXTP, already yesterday was presented, but even with the large area detector and the wide field monitor, you would scan the sky and have at least 10 observations. These are simulations that we did for the white paper in several areas of the sky. You will have large sample of objects in which we can extend this type of study. So I leave you with that, and I hope I convince you that we're finding that the properties of the object, even in a time domain, are remarkably constant, so the physics is the same. Thank you.
Questions?
Maurizio, which is the best energy band in which you prefer to measure this kind of variability?
Well, in this case, it's usually the hard 2 to 10 kV band, in which you suffer less, of course, of absorption. So if you can go rest frame for this band, for instance, under the field south, we use the rest frame 2 to 10, and also in Cosmos, it's obviously better. Although if you use the softer band, usually this kind of study don't suffer too much. You know, there will be exceptions, but on average, it's not that. But it's been shown that it's rather robust as well, if you really are photon starved.
So how variable absorption can affect the variability?
Well, it will introduce an additional component on top of that, in the soft band, of course. So for some, these objects are usually mildly absorbed, between 10 to the 22, 10 to the 23. So you expect to have some of that superimposed. But the point is that when you use this large sample, you're averaging over a number of these properties, and if it's fast variability like clouds on year time scale, that's probably averaged out. So it will not affect too much.
Thanks.
Yes, Barbara. Well,
very quickly, Barbara.
So you don't make any selection on AGN class?
No, in this case,
Everything that's
in everything. Well, of course, we try to avoid the extreme object in the local universe, the well behaved object, and we didn't even try to select radio quiet objects. So the couple of radio loud that are in the sample that we know of more or less behave like the others. There's not obvious difference. Although in principle, if they're flaring, you want to remove them out from the sample.
Okay, let's thank Maurizio again. Now Riccardo Midday. You wish. Extreme variability and possible change in look nature of ISO 511.
Okay, hi everyone. I'm Riccardo Midday. I work at the Space Science Data Center of the Italian Space Agency and at the Observatory of Rome. And before I start talking about the ISO 511-G030, I wanted to warmly thank the organizers for giving us the opportunity to be here and enjoy a 3D conference finally. So today I will talk about the variability properties of a nearby AGN, a type 1 nucleus hosted in a spiral galaxies that from an X-ray perspective is quite bright. We have a sort of 10 to the minus 11 flux in the 2 to 10 kiloelectron volt energy band. And then this source was listed in the Ferro sample. The Ferro sample was presented in De La Calle 2010 and contained sources with a broad iron K alpha with significant larger than 5 sigma, this meaning that relativistic reflection was in place in these sources. Moreover, this object was also known to have a strong soft excess. And yes. So we are quite proficient in understanding what's going on by studying the X-ray spectra emerging from AGN. We know that the primary power law gives us information about the hot plasma that comptonizes the seed photons emerging from the disk. We are quite good, but we still don't know actually what's going on with the soft excess. In fact, there are two possibilities to explain the soft excess, or blurred ionizer reflection or more comptonizations. And we're still debating on this issue, and we do not have a clear understanding of it. So imagine that we were trying to understand this point, and for this reason, we were looking for a source that was hosting relativistic reflection and a strong soft excess. So, ISO 511, it's sort of perfect source. As you can see here, we are dealing with, again, high flux AGN with a power law plus a soft excess. So we have two components here. For this, we were looking for this, and then we were awarding by a monitoring campaign involving XML Newton and Nustar data in 2019, at the end of 2019, and here what we got. So no soft excess anymore, but a power law. Just a simple power law, actually. But it's still interesting, because look at this. We had a drop in the UV emission, a drop in the soft X-rays that are sort of compatible. No, I don't know how to go back. While the hard X-rays were not as... I did. Thank you. While the hard X-rays dropped, but not by the same amount. So, we were not super happy, but however, we did our job. And to do that, we started by determining the timing properties of this AGN. And as you can see, everything is flat. We don't have variability in the hardness ratios, the last row. We don't have variability in the soft X-rays. We don't have variability in the hard X-rays. There is no intra-observation variability, and there is super small variability among the observations. And that was not really what we were looking forward, because, in 2007, the XML Newton observations, these are the corresponding light curves, were showing a different behavior. So hard X-rays and soft X-rays were varied, not in a compatible way. In fact, we are looking at the hardness ratio in the third panel that is changing during the observation. So, I mean, we were not that happy. But, again, from the light cars, we are able to get information about the undergoing physical process of AGN, and in particular, if we compute the fractional variability spectra for this source, in general, but I mean, for this source, we computed the fractional variability spectra and tried to understand what was behind the variability. And in 2007, we obtained that two components were needed to account for the variability process that was occurring there. On the other hand, in 2019, a single power law was enough to account for the whole variability of this object. So it's sort of, we don't have anymore a soft excess. So we started with two components, and now we got just a single power law. Okay, this was the first step in our understanding of this object, and we started with the spectroscopic properties, and we started from the iron K alpha. So as I mentioned, this source was listed in the ferro sample. So we were expecting the broad iron K alpha to be there, and we found it. And you can see in the contour plot that the normalization of the line from 2007 up to 2019 varied. And then we found that actually to reproduce the iron K alpha in this source, we needed a broad component, variable in terms of normalization, plus a narrow core. So if you have a narrow core plus a broad component, you may expect the overall emission spectrum of this AGN to have a complex reflection. So we ended up by using this model to model the 0.5 to 50, I guess, kilo-electron volt spectrum, so nu-star XMM Newton data. And we use a continuum emission, accounting for the hot corona, the hot corona, and we have a tentative estimate of the energy cutoff, not really trustable in my opinion, plus a cold component that accounts from, that I mean, is due to Compton material that accounts for a sort of Compton amp that we don't really have in this object, plus a not component, a reflection component that is likely emerging from 10-ish RGs from the disk, and it's Compton thick material. We were not super happy in principle, so we said, okay, this is just a model we can use. Let's try other models, but then we found out that we were able to rule out models in which the reflection was only due to a component, a relativistic one, so emerging from the disk, Compton thick, or both the narrow and the broad components emerging from the disk itself. So we tried RelXil plus silver, RelXil plus BB, and I mean, they were not as good as the model I'm showing you. Do you model the OM data plus the XMM Newton data plus the nu-star data with a single model? And actually, this is the case of AGN SAD. This model was proposed by Kubota and Chris Dunn in 2018, and essentially accounts for the whole emission spectrum of an AGN, in this case, from the ultraviolet up to the hard X-rays. And look how, I don't know if, yes. So here are the models we use to model the data that are quite well modeled, and you can see different things. For instance, first of all, the relativistic reflection varied a lot. The distant reflection was constant among these years. We are sort of 15 years, 15, yes. And then the power law here is quite hard. Here it's more flat, it's more softer, and then there is no soft excess. Here there is soft excess, and the UV here are mainly driven by the AGN. While in this other case, we needed to add a Galaxy template. So it's sort of, in 2019, the AGN was not driving the UV emission. And this can be somehow explained. I mean, the drop in Eddington ratio that is accounted by it's reported by the model, so it's about a factor 10, may explain changes in the inflow of this AGN. So in 2007, in the case of a standard, let's say, disk, work optimization, if we trust work optimization, but just disk soft excess and hard power law, we are dealing with something that is quite, let's say, standard. If you see the paper by Stefano Bianchi or Enrico Piconcelli or Liozzi 2020, I mean, if you study X-rays spectra of IGN, you will always find a soft excess. But then if you don't find it, I mean, it's sort of strange. And in accordance with this model, we obtained that there was not a region accounting for the soft excess. So just disk plus hot corona. And I mean, the fact that we are dealing with a lower Eddington cools down the corona, and that's why we have an harder behavior. So is this plausible? Yeah, maybe. And yes, I'm almost there. And to do that, we, no, here. And I mean, we also studied this source via 2 monitoring campaigns. The BI was Enrico Piconcelli and me. And we were, trying to understand what was going on in X-rays and UV again on different time scales. And consider that this monitoring campaign covers the XMM Newton Nusser observation. So they start from 2019. And I mean, you see a sort of sad X-ray light card that is not that variable. Here the photon index is always sort of constant and significantly hard. And the UV are telling us the very same history. It's not something that is really going on there. And I mean, try to compare these SID from the soft excessed XMM Newton 2007 observation with those we obtained after the monitoring campaign of 2019. You see that from something that was sort of flattish and compatible with the one by Richards, we had a significant slope. And I mean, here it's just a way to show that we were dealing with something that was really variable in the UV more than in X-rays. And up to 2019, the UV emitted by the IGN were galaxy dominated. So the UVs from the IGN were not that significant. The galaxy was really leading the UV emission in our case. And you can see a track of the variability of the alpha X. But I told you that we may be on the verge of a changing look. From 2022, we see that there is an increase of the UV flux, to which correspond a sort of increase of the SID. So I don't know if we will be able to observe a revenant soft excess in this object, but in case, I suppose that a recovering UV emission will lead it. So thank you for your attention.
Questions for Riccardo?
It's more a curiosity. I want to know if you had the optical spectra of this object during any of this time.
Yes, we had one, and from Floyd. And are you maybe interested in the H beta? But I mean, we found that the H beta was still broad at the time. So we were just looking for the H beta. We got an optical exposure of it, and the H beta was broad. Just this. I don't remember actually, but broad enough to say that it was broad.
So based on this behavior, what do you think is the origin of the soft excess?
Okay, so the recent papers by, I think that the soft excess is a mixture of relativistic reflection and work comptonization in general. In agreement with this behavior, I would say that if you don't have enough accretion power to sustain the warm corona, as demonstrated by simulations by Bob or David Ballantyne, you don't have the possibility to get this warm corona and the soft excess. If the soft excess is mainly driven by relativistic reflection, relativistic reflection is still there. So why we don't see it anymore? So in this case...
Don't ask me.
Yeah.
Okay, let's thank Riccardo again. We are now moving to the first session of flash presentations for the posters. A few tips, 2 minutes sharp.
So please,
you can all approach here because the slides will change.
So I ask all the flash poster speakers to come and just be
Baldini,
live
Barchiesi,
here.
Bartolini, Belladitta, Bronzini, Diana, and Igina.
And I think Riccardo was the only one who didn't require a mic to speak. So this is how it works. So I will start from the first. This is for you guys. So I start from the first slide, and I will move regardless if you finish to speak or not after 2 minutes. I have no mercy, okay? All right.
Okay. So hello everyone. I'm Sara Baitieri, and I'm a master's student at the Milano Bicocca University. I worked on this poster with Patrizia Romano, Stefano Vercellone, and Luigi Pachani, and is about the multi-wavelength properties of a small sample of gamma-ray narrow-line Seyfert-1 galaxies. The sample is made of 3 sources that were taken from the ones listed in Romano et al. 2018, and they've been observed with Swift, UVOT, and XRT. And in particular, these observations were taken at very regular time interval of around a week for a total time period of a year. So in this way, we were able to eliminate any type of biases towards, for example, follow-up observations. So we studied their light curves and their variability in the 7 energy bands, 6 for UVOT and 1 for XRT. And we studied their variability by calculating a couple of parameters, which are the dynamical range and the fractional variability amplitude. We also started applying the Bayesian blocks method to the light curves in order to determine the duty cycle, to individuate the flares, and also to try to predict how many flares each source does in the 1 year time period. And lastly, we started studying a second sample of 8 sources, which have been reclassified as gamma-ray narrow-line Seyfert-1s, so that we can compare their properties in the X-ray, UV, and optical energy bands to the ones of the sample we have already studied. And about this last point, I have a surprise on my poster. So if you're curious, you can come and see my poster tomorrow to find out what it is. And thank you for your attention.
Hi everybody, my name is Pietro Baldini and I'm a master's student from Bologna University, and in my poster I'm presenting my master's thesis, which is currently ongoing under the supervision of Marcella Brusa. So we're studying 2MASS 0918, which is an AGN that between 2003 and 2005 underwent drastic X-ray spectral variation, as shown by 2 XMM Newton observations, going from a highly obscure state into an unobscured one, increasing its flux by 1 order of magnitude, and also revealing the presence of a UFO in the unobscured spectrum. This all suggests that we're observing the source in its blowout phase, in which the AGN clears its surroundings from obscuring material through powerful winds. In order to confirm this scenario or to confute it, we have first of all performed SED fitting, through which we have strong constraints on bolometric luminosity and also host galaxy properties. And then we've taken the also available 2005 SDSS spectrum, which also shows asymmetric line profiles, which are an indicator of outflows also in the ionized phase. And we have, through multiple Gaussian component fitting, we have obtained the outflow velocity and the mass outflow rate. But the focus in the next few months will be actually on high energies, as we have dedicated follow-up XMM Newton and NuSTAR observations that were taken in 2020, through which we will fully characterize the UFO, and also with this data together with the original ones and also Swift XRT data and data from the first 4 Rosetta Sky surveys, we're planning to build the light curve and to assess whether the obscuration was actually the cause for the variability, or understanding in general what's going on with this source. Thank you for the attention.
Hello, I'm Luigi Barchesi, and this is my work about the study of a sample of neon-5 selected obscured AGN. And we perform an X-ray spectral analysis for the X-ray detected sources, plus for all the sources SAD fitting and comparison with a parent sample of non-active galaxies. What we found is that our sample is, a lot of sources in our sample are very obscured, like 2/3 have NH greater than 10 to the 23 centimeters to the -2, and that a lot of sources are in a strong phase of accretion from their Eddington ratio. The comparison with the parent sample told us that our sample seems to lack a population of low specific star formation. So there are less quiescent galaxies than with respect to the parent sample. And finally, drawing the conclusion, we can say that the neon-5 is an excellent tool to select AGN in the obscured accretion phase, and that it seems that we have a higher efficiency in forming stars with respect to non-active galaxies.
Hi everyone, I'm Bartolini Vieri, and today I will present to you briefly my work that I performed with Professor Dalla Casa, Dr. Giroletti, Dr. Gomez, and Dr. Lico. And it revolves around the multi-wavelength simultaneous VLBI view of 3C111. That is one of the radio sources with the brightest core at millimeter wavelengths. And we performed an analysis in which we managed to produce total intensity images for all the 6 frequencies, and moreover also the spectral index analysis. And all these can be found in my poster. In addition to that, we also managed to found 53 components at different frequencies, thus confirming the richness of these jets. And by taking into analysis the physical properties of these components, we found some interesting relationships. For example, the one that characterized the brightness temperature and the equipartition magnetic field, which seems to be really strong, and suggested that the brightness temperature scales as the equipartition magnetic field to the power of 2.63. In addition to that, we also perform polarization analysis, and we found a rotation measure between 5, 8, and 15 gigahertz. And with applying the correction, we could see that the EVPAs are suggesting an helical structure. If you have any questions or curiosity, I will be more than happy to answer that. And thank you for your attention.
Sorry for the colors, but it's not the real color. Sorry. Okay, so my posters show the discovery and properties of the new powerful and likely young radio light quasars at redshift 5.3, PSO J191. And okay, skip, thank you. The main characteristic of the source is that you show a peaked radio spectrum, so the source can be classified as a GPS, a gigahertz peaked spectrum source. And so GPS are very important sources in the field of radio galaxy evolution because are considered to be the young stage of large-scale radio galaxy. And so detailed study of GPS could shed light on the triggering radioactivity on the first stage of evolution of jets, the interaction with the environment, and the feedback on the host galaxy. But since variability could affect what we observe in the radio band, we have an approved VLA follow-up on a wide range of frequency to confirm or not the turnover. If this turnover will be confirmed, this source will be one of the youngest GPS at threshold above 5 ever discovered. And also we have a VLBA follow-up to reveal the parsec scale structure of the source. And you can see there the C-band image at 5 gigahertz. You can see the source is compact but marginally resolved, seems to have 2 little extension, one in the west-east direction and one in the southeast direction. So that could be the newly born jets, but the analysis is still in progress, and so we have to wait for the other images that we have, and for all the details of this source, come up there to see the poster. Thank you.
Hello everyone, my name is Ettore Bronzini and I'm a graduate student at the University of Bologna, and today I'm going to briefly talk about my master project titled Investigating High Energy Emission Young Radio Galaxies. In the context of radio galaxies, some of the most intriguing questions are related to the early stages of their life. The so-called compact symmetric objects are thought to represent the first step in the evolutionary path of these sources. We can consider them the screaming babies, And just to give you an idea of how these sources look like, this is the image of 1146 in the radio band. No, sorry, but it doesn't matter. Sorry, in the radio band, where you can see a clearly detected core and two jets, and on the right you can find Chandra view. Obviously, is not resolved in X-rays, and it is a point like. Okay, these are just a few analyses I performed. I started with the X-ray analysis of the Chandra and new star proprietary data. And then I moved on the SED modeling of the source. And I also investigated the role of the ambient medium in confining the source expansion. The red circles are just some spoilers about my results, but if you want to know more about it, you can find me with my poster upstairs or on the beach this afternoon, without poster, obviously. And that's all.
So, hi everyone. My work is about the evolution of the heaviest supermassive black holes hosted in jetted AGNs. And we started from a well-defined blazar sample with redshifts ranging from 1.5 up to 6 and selected in radio frequencies. Then, after gathering all the optical spectra, we calculated the masses of the black holes inside those objects and selected only those with a mass greater than 10 to the 9 solar masses. Then we counted every of those objects in each redshift bin in order to calculate the number density of those blazars as a function of redshift. And after that, by assuming an average viewing angle for the blazars, we were able to integrate on the whole solid angle in order to obtain the jetted AGN number density as a function of redshift, of course, for the objects hosting massive black holes with a mass greater than 10 to the 9 solar masses. And the result can be seen on the plot on the right, with the golden curve representing the jetted AGN number density, the purple points representing the blazars from which we derived the golden curve, and finally the blue curve representing a quasar luminosity function integrated from the minimum luminosities of our sample up to infinity, which should include all the AGNs with similar masses. And as we can see, the two curves looks very similar in shape, although we can see that the yellow curve peaks a little early, and this can be actually quantified to be 500 million years at least, and therefore pointing to different evolution for jetted AGNs compared to the total population. For the details, I wait you upstairs at my poster.
Yeah. Okay. Anyways, I have two posters, so I didn't prepare this one, but I'm gonna try to talk about this. I can do it. Okay. So in this poster, I'm trying to summarize the project that we are currently doing. Basically, we're trying to expand current samples of radio loud AGNs, a redshift above 5, where only 20, 30 sources are known. In particular, we want to do this in a statistical way in order to have a statistically complete sample. This will be very useful for many different reasons. The first one being that this sample will be crucial to constrain the deformation, the evolution of supermassive black holes hosted in systems with powerful radio jets right after deformation. And also for other reasons, for example, you can find them in my other poster, which I'm going to talk about tomorrow, apparently. And how we did it, our work is based on the RAX survey, which is the first all-sky radio survey performed with the ASCAP telescope, the SKA Pathfinder. And in the poster, I'm showing that the first results, which are mainly we were already able to identify 3 new redshift radio loud AGNs above redshift 6, where only 4 other are confirmed so far. So, and you can find this poster if you're interested at the bottom of the Altana. It's really the last one, and I'll be there. Thank you.
Okay. Yeah.
This morning. I remind you that today you have a free afternoon. For those who want to play and haven't collected the jersey, come to me on the stage. For all the others, see you at the social dinner. Maybe you want to add.
I just want, before you leave, people that want to attend the social dinner. So the social dinner starts at 8. So please come on time. And people that have have notified us for allergens or lactose-free or any other thing, you should write this up in your tag that we provided to you. And notify the waitress on the way there when you are at the restaurant. I also ask the flash store speakers of tomorrow. Can I have your attention? I know not many of you. So the flash speakers of tomorrow, please remember to introduce yourself before you speak. Otherwise, people will know. If you don't write the name of your name in your poster, nobody will know who you are. So just introduce yourself before you start speaking. So see you all either at the football match or both at the social dinner.